Hello, I'm Mirdad Simkani, your college algebra professor, and this lesson is about rational functions. A rational function is a ratio of two polynomials where a polynomial is a linear combination of whole powers of x, like x squared, x cubed, x to the 1, constants. You add them all together, multiply them by coefficients, and then add them together, you form a polynomial. Let's see some examples. We have studied polynomials, so this is a little review. So these are polynomials. The ones, see, these arrows indicate that this keeps going up forever. Here goes down forever. So the ones that go up and down on the sides, both on one side go up, on the other side go down, these polynomials have odd degree. So these ones have odd degree. The ones that on both sides either go up together or they go down together, those have even degree. Like x squared, for example, which is a parabola. And the minimum degree, we have done these exercises before, is to just count the number of turning points, 1, 2, 3, 4, 5. So this one is at least 6 degree. It could be 8 degree or 10 degree and so on. So we have done all that. And also we know that the domain of all of these polynomials, there is no restriction on x. X can be any real number, right? Every time you raise a real number to a power, that's still a real number. So there's no, and when you add them together, they're still defined. So there's no restriction on what x can be. So the domain, we say, is from negative infinity to infinity. So that's what we know about polynomials, and you've done lots of exercises answering different kind of coefficients. So now let's look at some rational functions. That is the subject of this lesson. So here there are 3 examples. A rational function, again, is a ratio of two polynomials. Here, for example, f has a degree 4 in the numerator, a polynomial of degree 4, and denominator is a polynomial of degree 2. This particular one, because denominator can never be 0 for any x, because x squared plus 5 is always 5 or higher. It can never be lower than 5. So that makes the domain for that polynomial to be all real numbers. That's for f. And the graph of that looks like a polynomial. Like this is very smooth and just like polynomials. The other ones, like this one, for example, g, it has a denominator that may be 0, and it is 0 in this case, at, if you factor it, first of all, it's a degree 3 over degree 3. And you know how we determine that x minus 1 is a factor. If x equals 1, so what do we have? 2 times 1 cubed is 2, minus 1 squared is 2 minus 1, and the minus 1, you have 2 minus 2, which is 0. So that's how we know x minus 1 is a factor. And then if you divide 2x cubed minus x squared minus 1 by x minus 1, you get this as a quotient, 2x squared. You get 2x squared plus x plus 1 And now we can check it actually. If you want, you can check. Multiply 2x squared by x, you get 2x cubed. 2x squared by minus 1, you get minus 2x squared. And now x times x is x squared, with the minus 2x squared gives you that minus x squared. And then x times minus x is minus x. 1 times x is positive x, with the minus x cancel out. 1 times 1, negative 1 is negative 1, so that checks. Now these, when the denominator is negative 1, x is negative 1, in the denominator you get a 0. So this function is not defined at 1. And if the quadratic factor here is also factorable, then you have 2 more zeros, or maybe if it's a completed square, you would have just 1 more 0 in the denominator, so it would be undefined in 2 places. But this one, if you try the quadratic formula, let's see, if you set this equal to 0, by quadratic formula you have minus 1 plus or minus a square root of 1 squared, which is 1, minus 4ac, 4 times 2 times 1 is minus 8. So you have a negative quantity under the radical, so that is not factorable. So the only place where the denominator is undefined is 1. And if you really need to know, denominator is 4 because 2 times 2. So the domain for G is negative infinity to 1. At 1 it's undefined, and then union 1 to infinity. In fact, you can see the reason the function breaks up into 2 pieces, so this is a discontinuous case. The one above was continuous. It was just like all polynomials. So this one is discontinuous at 1. So we can actually get the, there is a line that separates the 2 pieces, this line here. This line has equation x equal to 1, and this line is called a vertical asymptote, and the property of the line is that as x gets close to 1 from the right or from the left, the graph gets close to this line, and that's what we call a vertical asymptote. Also, due to the fact that the numerator degree is less than or equal to the denominator degree, that makes it have another asymptote which we call a horizontal asymptote. And in fact here that asymptote is this line here. So what does that mean? Let me explain that. So there is a line that as x goes to positive infinity, to the right forever, or to the left, this horizontal line, which we call a horizontal asymptote, again divide the graph, one piece. Actually, it is possible that the graph crosses this horizontal line and then goes back up and then back down. It is, the function could behave that way, but the point is, as x goes to positive infinity, the graph gets close to that line, just like the vertical asymptote. As x gets to close to 1 from either side, the graph gets close to this line. And also, as x goes to negative infinity, the graph gets close to this red line, which we call horizontal asymptote. And that is only if, and in fact, that is only if the degree of the numerator is not greater than denominator. If the degree of the numerator is greater, then it has some other kinds of asymptotes. They're called slant asymptote. If the degree is 1 more, if the numerator is degree 1 more, then that slant asymptote is a straight line. As the graph goes to positive or negative infinity, as x goes to positive or negative infinity, the graph gets close to that line. And if in this case the degree of the numerator is 2 higher, and then the graph would approach a quadratic polynomial on either side as x goes to positive or negative infinity. So that's about that. Now, for the last, there are more examples to come, but this one has actually 3 asymptotes. If you factor the denominator, first of all, notice that if I let x be negative 1, when you plug in negative 1 for x, you get negative 2 here and positive 3 and a negative 1, that would be 0. So one factor of this polynomial is x plus 1. We talked about the factor theorem before, so that's how we know this is a factor. And then the quadratic factor that is multiplied by that to get 2x cubed minus 3x minus 1, we can actually construct it either by divide 2x cubed minus 3x minus 1 by x plus 1, or just here guess what you would need to multiply by x to get 2x cubed. If I multiply 2x squared by x, you get 2x cubed. And then 2x squared is also multiplied by 1. There is no squares here, so I have to subtract it. So if I subtract minus 2x, then this minus 2x times x will give me the minus 2x squared that cancels the other 2x squared. Now the minus 2x is also multiplied by 1. So that would give me minus 2x. But I need minus 3x, so 1x is short. So I need a minus 1 here. So after I multiply by this x, that will give me the minus 3x. And also check the last term. Minus 1 times 1 is minus 1. So I did this correctly then. That would be a good test. Here, the 2x squared minus 2x minus 1 also has roots. We can find them, and they are by using a quadratic formula for this. So if I use the quadratic formula, first of all, from that I get x equal to minus 1, and then when I apply the quadratic formula here, I get 2 plus square root of 2 squared, which is 4, and then minus 4 times 2 times minus 1 is minus 8. I have to subtract it, so it's plus 8, divided by 2 times 2, which is 4. And that gives me 2 divided by 4 is, I can reduce it. And then first figure out what is the other one. The square root of 4 plus the square root of 4 plus 8 is the square root of 12, right? And 12 is 4 times 3. The square root of 4 is 2, so there is a factor 2 here and then 3 inside. But when you divide everything by 2, so this 2 becomes 1. I forgot the minus, didn't I? So it should be 2 plus or minus. So I have a plus or minus square root of 3 because the 2 is simplified with the 4. So this is what I get. I get three numbers. 1 plus the square root of 3 over 2, 1 minus the square root of 3 over 2, and minus 1. And these are the numbers that you cannot have x equal to. because that makes denominator 0. So the domain of this function, the domain is from minus infinity to the smallest of these three. You see, square root of 3 is about 1.7. So 1 minus that with about minus 0.7, and divided by 2 is bigger than minus 1. Minus 1 is the smallest of the three roots. So from negative infinity to minus 1, union, now from minus 1 to the next root of the denominator, which is the smaller of these two, would be 1 minus. So 1 minus the square root of 3 over 2, and then union 1 minus the square root of 3 over 2 comma to the next root, which is 1 plus the square root of 3 over 2, and then finally union from 1 plus the square root of 3 over 2 to infinity. So this is the domain of the function h. Now let's look at the vertical asymptotes. At every one of these three numbers, at negative 1, 1 plus the square root of 3 over 2, and 1 minus the square root of 3 over 2, at all these three, you have a vertical asymptote. So here, where they are, at negative 1, I think that would be about here, right? That's 1. And then you have the next one here. This is the one with the minus 1 minus the square root of 3 over 2. So that's is about here. And then the third one is 1 plus the square root of 3 over 2, and that would be here. So these are the three vertical asymptotes for this function. Something to note here: the numerator is not 0 at the same time the denominator is. You know, the denominator is 0 at these three numbers. Any of these three you put in the numerator the numerator would be 0 at negative 4/3. Otherwise, the factors, after you factor the numerator, they have to cancel out. After you cancel out the factors, then you decide what the vertical asymptotes are. Here too, the only vertical asymptote was at x equal to 1, and 1 doesn't make the numerator 0, so that's why x equal to 1 is still an asymptote here. And about the horizontal asymptote of this one, when the degree of the numerator is less than the degree of the denominator, in the long run, the denominator gets a lot bigger, a lot faster, so that's why this will go to 0. So that's why the horizontal asymptote is 0. So let me label these. This is a vertical asymptote, this is a vertical asymptote, this is a vertical asymptote, and the horizontal asymptote is the y equal 0, the x-axis. So that's why when x gets large, this quantity would be close to 0, whether x is positive of a large number or negative of a large number. When you look at the other one, y is 5/2, which is 2.5. You see, that's the equation of that line is y equals 5/2. That's the horizontal asymptote, and that has a lot to do with these coefficients. That's when the degrees are the same. When the degrees are the same, you divide the leading coefficients, and that would be the horizontal asymptote. And that the explanation for that is this: if I choose a high number for x in each of the two polynomials, the leading term would dominate the rest, because x cubed is a lot bigger than 4x. X cubed is a lot bigger than x squared when x is big. For example, you don't even have to try a big number like 10. What is 10 cubed? Is 1,000. What is 10 squared? Is just 100. Now imagine you have more zeros. So this has 3 times the number of zeros in x. The other one has 2 times the number of zeros of x. And in the long run, this x cubed beats x squared and so on. So therefore, the ratio, the x cubed and x cubed, those two terms decide what the horizontal asymptote would be. And that's why you get 5 halves. For this case, when the numerator is just x, denominator is x cubed, you can tell denominator gets a lot bigger faster than x, and that's why 0 was the horizontal asymptote. Now let's look at another example here. This one, again, the denominator is exactly as the previous example. So this is still x plus 1 in the denominator times 2x squared minus 2x minus 1. So you can tell that, you see, compare this with the one above it. Notice that 2 of the asymptotes are about, actually they're exactly the same here because those are the roots here. Those are the roots of this one, not the root of the other. So in this case, you see the x plus 1 and x plus 1, you cancel them out when you're deciding on the asymptotes, for the asymptotes. But for the domain, you're still included. So let me write the domain first. So the domain here is still the same as all of that. So it's minus infinity to minus 1. And this one has the same roots as the one above. Because it's the same polynomial, I just want to write them over here. 1 plus or minus the square root of 3 over 2. Those are the two roots. And then the other one is a 1. Negative 1. So these are the 3 roots in the denominator. So you can still not divide by 0. So the domain is from minus infinity to minus 1. Union minus 1 to 1 minus the square root of 3 over 2. Union 1 minus the square root of 3 over 2 to 1 plus the square root of 3 over 2. Union 1 plus the square root of 3 over 2 to infinity. I hope I got all of them. So that's the domain. Now, why are the asymptotes only 2 of them? So it only has 2 of those asymptotes. Here's 1. Over here. And this is the other one, which will be over there. And these go with these 2 numbers. So we go with, so this one will go with this, and the one with minus would go with the other asymptote. So those are the 2 asymptotes. And then the x plus 1 disappeared only because these x plus 1s are cancelled. Still, the difference between the domain and the vertical asymptotes is that for the vertical asymptotes, you cancel those factors. But for the domain, you keep it because it's still in the denominator. You can still not plug in negative 1 for x. So that's the difference between vertical asymptotes and what you exclude from the domain. So here's another example. The denominator is, look, this is the one after you cancel x plus 1s. After you cancel x plus 1, notice that 2x squared minus 2x minus 1 is in the denominator here. And now the graph is exactly the same. The asymptotes are exactly where they should be. They're the same. So the difference is there should be a hole here at -1. You see, at -1, there should be a hole in the graph. But the computers ignore those things. So this graph is generated on a computer. That's why computers don't do that. But if you do this by hand, you're expected to note that x cannot equal -1. But this one, in the graph in the bottom, has no factor x plus 1 in the denominator. So it's continuous at -1. That's the difference between j and I. They're not the same function, but they have the same vertical asymptotes. All right, so here's the last slide. It summarizes the stuff we just talked about. Rational functions are not defined where the denominator is 0. The domain of a rational function is a set of all real numbers except the zeros of its denominator. Before you factor and cancel, before you cancel the factors from numerator and denominator, if they are common factors. Vertical asymptotes are at the zeros of the denominator except for the factors that are cancelled, okay, from both numerator and denominator, as I showed you before. And the equations for vertical asymptotes, you write them as x equal to some constant, like I wrote here for vertical asymptote, x equals 1, okay. For horizontal asymptote, you write y equals, or y equals some constant. What is a horizontal asymptote? They do exist. A horizontal asymptote exists only if and only if the degree of the numerator is less than or equal to the degree of the denominator. If the degree is strictly less, not equal, then y equals 0 is a horizontal asymptote, like we saw here, like this one, I, and also h. The degree of the numerator is less, so the horizontal asymptote is the x-axis. But for g, the degree of the numerator and denominator are different, and in that case, I'm sorry, I had to shut my phone off. The degree is the same, so the ratio is that horizontal asymptote, 5/2, y equal 5/2, and that is summarized here. And this concludes this lesson, so I can go answer my phone. Sorry. Excuse me, sorry about that. There will be more lessons for the future or the next unit later on in the course. So I think this is the last lesson for this unit. There will be a Zoom session that I will work out some problems for this unit next week. So I will announce it.